In our last couple of videos, we've been talking about local stability. So if you start near an equilibrium point, do you stay near it as time continues to go on? Today we're going to be talking about global stability, and obviously things are going to be slightly different because we're going to have to deal with the fact that you can start from anywhere if you're talking about global stability, and so we need to properly define what we mean by all of these terms. So let's go ahead and get started by defining, let me give myself some lines. Let's define what we mean by globally attractive and globally asymptotically stable. So globally attractive will mean that, well, starting from anywhere, you're going to go towards your equilibrium. You're going to eventually limit to your equilibrium as time goes to infinity. And globally asymptotically stable is if it's both globally attractive and locally stable. So to make that a little bit more precise, let's suppose that x bar is an equilibrium. X bar is an equilibrium of a first-order difference equation of the difference equation, nonlinear in general. X sub t plus 1 is equal to f of x sub t. So the standard setup, where we're going to have f be a function from 0 to a to the same interval, 0 to a, where a could be infinity or it could be some smaller number. But the important thing here is we're going to restrict it to be positive. This is in general not necessary for difference equations, but since this is a mathematical biology class, we don't actually care that much about negative numbers because, well, you can't have a negative number of rabbits in an ecosystem. Many of these results are also general, even if you allow for negative numbers, but we're not going to deal with that. So if we have the setup, then x bar is said to be globally attractive. If for any x naught in our interval, 0 to a, the limit as t goes to infinity of x sub t is equal to x bar. So note that this is very similar to locally attractive, except we don't have to worry about starting near our equilibrium. We can start anywhere in our domain. And furthermore, we're going to call it equilibrium x bar is globally asymptotically stable. If it is globally attractive and locally stable. Okay, and recall locally stable just means that if you start close to x bar, you stay relatively close to x bar. And we talked about the formal definition of that a couple of videos ago. So now, as an aside, if f is continuous, then globally attracting implies locally asymptotically stable. So if our function f there is continuous, then we don't have to worry about these several different definitions because the moment it's globally attractive, then it is also asymptotic. It's also locally asymptotically stable and therefore also globally asymptotically stable. Let's give a easy result for when a difference equation is globally asymptotically stable. So we're going to say if f from 0a to 0a is continuous, and that we have 0 is less than f of x is less than x for all x in 0a, then the origin is globally asymptotically stable. Okay, and the proof of this is pretty straightforward. So x0, x1, and so on is monotone decreasing and bounded by 0. And 0 is also the only fixed point by supposition. Because one of our assumptions is that for any x that isn't 0 in our domain, f of x is smaller than x. So they clearly can't be fixed points. And so therefore everything has to go to 0, and then we're done. Now that's not a particularly interesting example, but that is a useful one. It basically means that no matter what you start out with, you eventually die down to 0. In a more biological context, this might be some species that just doesn't have a chance to live in some environment. You introduce some number of them, and then they all die out. Let's give a more interesting theorem, and this is fairly general, though the conditions are a little bit technical. So let all of the following conditions hold. And I'm going to number them because we're going to reuse some of these conditions later. So let's say 1, f is a continuous function. Function on 0a. And a is greater than 0 and less than or equal to infinity. 2. F goes from 0a to 0a. And 0 is less than a is less than or equal to infinity, as before. And C3, f of 0 is equal to, I'm actually going to give this a color because we're going to refer back to this later. So 3, f of 0 is equal to 0, and f of x bar is equal to x bar are the equilibria. We don't actually need to write this because that will be, those are both equilibria. 4, f of x is greater than x for x greater than 0, less than x bar. And f of x is less than x for x bar is less than x is less than a. And you note that this implies that those two are our only equilibria because everything else doesn't remain constant. And 6, and this is a slightly more complicated condition. So if there exists some x sub m in our interval, in the interval between 0 and x bar, such that it's a maximum, so such that f of xm is equal to the supremum over x in 0 x bar of f of x. So if there exists a maximum, then f is decreasing. Let me write this over here so I'm not squeezed for space. Then f is decreasing for x greater than this maximum. Okay, let me put this in parentheses. X sub m is a maximum in the interval 0 x bar. Okay, so if all these, when all conditions 1 through 6 hold, then x sub t plus 1 is equal to f of x sub t. So given this difference equation, has a globally asymptotically stable equilibrium at x bar if and only if f has no 2 cycles. And let me go ahead and put an important note here, just to clarify. F decreasing is not equivalent to saying f of x is less than x. This is a very, very different condition. One of them is the application of x. The other is as x gets larger, what happens to f. So, for example, if we have our y equals x lying here, and we have f of x here, decreasing on this range, but f of x is greater than x. So just keep that in mind when you're understanding these things. So now, the proof of this is pretty onerous, and so we're not going to get into it. We'll go into some of the other proofs of some of these other global stability theorems, but this one is rather long. Obviously, if there is a globally asymptotically stable equilibrium, then there can't be a 2 cycle. That direction is easy, because if you had a 2 cycle, it wouldn't limit to one of your equilibria. It would just keep on bouncing back and forth. The other direction is a lot more work. And we'll see some proofs that are similar, though we won't actually prove that one. And just to give a little bit of an illustration of things that do satisfy this, I'm just going to draw a couple pictures. And so each time I'm going to have the y equals x line. And so if we have a function that looks like that works. You can do something like this. And you can also do something like that. So those all satisfy the conditions that we described above. And we'll see, if you wait for the next video, we'll actually walk through an example of an actual equation. But these are some pictures, just to give you some intuition of what's happening. So each of these has a global asymptotically stable equilibrium at that point. Actually, let me fix this a bit. Let's make this clear that this is not a maximum. So it can do whatever it wants afterwards, but you need to make sure that there isn't actually a maximum before you reach the equilibrium, or things might go super weird. And actually, let me make sure this is continuous as well. So let's say that goes there. Yeah, you don't want to, if you introduce discontinuities, then all bets are off. Okay. Now, sometimes finding 2 cycles or proving the non-existence of 2 cycles is a pain. You can obviously do it by setting f of x is equal to x, but is there an easier way to do it? And in certain cases, there is. So that's the subject of the next theorem. This is 2.7. So we're going to let f prime from I to I be continuous. So if we have a continuous first derivative, if 1 plus f prime of x is not equal to 0 for all x in I, then x sub t plus 1 equal f of x sub t. So this difference equation has no 2 cycles. Has no 2 cycles in I. Oh, and we can prove this. So suppose that there does exist a 2 cycle. So this is going to be proof by contradiction. So let's suppose there exists a 2 cycle x0, x1, such that f squared of x0 is equal to f of x1 is equal to f x0, and x0 x1 are in our interval. Well, then we know that the integral from x0 to x1, I'm going to go assume without loss of generality that x0 is less than x1. So without loss of generality, we know that x0 is less than x1. Because they go back and forth, so you can pick whichever one is smaller to begin with. Of 1 plus f prime of x dx. Well, that is, of course, equal to x1 plus f of x1 minus x0 plus f of x0, which is equal to f of x0 plus x0 minus x0 minus f of x0, which is equal to 0. But then, by the mean value theorem for integration, by the mean value theorem for integrals, there exists some c in this interval such that 1 plus f prime of c is equal to 0. But now this is a contradiction. So this is a contradiction. And so our assumption is that it's not equal to 0 for all things in our interval I. Hence, there are no two cycles. So now, one example of an easier condition to check than actually checking all 6 of the conditions that we talked about in Theorem 2.6. There are a couple other simpler things of way of checking global stability as well. And let's go through another one here. So this is going to be Theorem 2.8. And this is going to be analogous to Theorem 2.5 in terms of how we're going to prove it. We're basically going to prove that, so in Theorem 2.5, we basically said that if all of our values are decreasing, every time you apply f of x, you decrease the value down to 0. Well, then 0 is globally asymptotically stable. Theorem 2.8 is similar, but just instead it goes in both directions to some value x bar that's not equal to 0. So let's see. If f is our function on the domain 0a, and it's continuous, and we know that x bar is in 0a, such that x is less than f of x is less than x bar for 0 less than x bar, and we have that x bar is less than f of x is less than x for x greater than x bar. Then our favorite difference equation, the difference equation, x sub t plus 1 is equal to f of x sub t, has a globally asymptotically stable equilibrium at x bar. Asymptotically stable equilibrium at x bar. And the proof of this will be very similar to the proof of 2.6 a little bit ago. Basically, you just take these sequences and limit. So first thing to note is x sub t is less than x sub t plus 1 is less, which is because that's equal to f of x sub t is less than x bar for x sub t is less than x bar. And x bar is less than x sub t plus 1, which is equal to f of x sub t is less than x sub t for xt greater than x bar. So we're just applying the condition on f to the value x sub t. Okay, so we have a couple cases here. So let's call this case 1. X naught is less than x bar. So our initial thing is smaller than x bar. Well, then we know that the sequence f to the t of x naught as t goes to infinity is of course just equal to this. We know that this thing is monotone increasing and bounded above by x bar. Because we said that you're starting small in x bar, and what we set up here is that if you start smaller than x bar, then the function can't ever get up to x bar because f of x is still smaller than x bar. So it's bounded above by x bar, and we're going, and so it limits to something, and so we don't know what that is yet, so we're going to call that z1. That's going to be the limit as t goes to infinity of f of t x naught. But of course, this is equal to f of the limit as t goes to infinity of f to the t minus 1 x naught, which is equal to f of z1, and so this is a fixed point. Okay, so it limits to some fixed point, and then we have case 2, which is that x naught is greater than x bar. Well, then we have the exact same analysis, but in the other direction. So then this sequence f, let's call this, yeah, so then this thing is of x naught, t0 to infinity. This is monotone decreasing, and still bounded below by x bar. And let's let this z2 be list bound. Would be list limit for things starting above x bar. And that turns out to be equal to f of z2, so it's also a fixed point. But the only positive fixed point of is x bar, so z1 is equal to z2 is equal to x bar. And therefore, whether you start below or above, you always limit to this one single fixed point. And so you get global asymptotic stability. And finally, I'm going to leave you with one other theorem on global asymptotic stability. This one is going to be, in some sense, a rephrasing of Theorem 2.6, where instead of our two-cycle condition, we rephrase it in terms of properties of f of x. So I'm also not going to prove this, since the proof is a little bit long, though you can find part of it in your textbook. I'm not going to expect you to know the proof for this theorem either. So if we let x sub t plus 1 is equal to f of x sub t, per usual. So there are two parts to the list. The first is a recapitulation of a lot of Theorem 2.6. So suppose f satisfies assumptions 1 through 5, but f has no maximum in the interval 0 x bar, then x bar is globally asymptotically stable. And B, suppose f satisfies. Let me actually copy the conditions. That might make things a little bit easier, just so that we can keep in mind what these are. Oh, I didn't get that this time. Let me try that again. Let's copy that, and let's paste that down here. Let me insert some space actually, and paste that down here. So just a reminder, so if we satisfy conditions 1 through 5, but it has no maximum, well, then x bar is globally asymptotically stable. Now, if suppose f satisfies all 6 of our conditions, satisfies assumptions 1 through 6, and f has a maximum xm in the interval 0 to x bar. Let me scroll up a little bit. Then x bar is globally asymptotically stable. If and only if f of x is greater than x for all x in x sub m comma x bar. Okay, so this condition basically replaces the condition about 2 cycles. And so this is sometimes a little bit easier to test, sometimes a little bit harder. But it is an alternative way of figuring those things out. In the next video, we'll actually go through some examples of applying each of these different theorems to determining whether or not a difference equation has a globally asymptotically stable equilibrium on the positive real axis. So I will see you in the next video.